Can you hear me? All right. Mm, anyways, so yeah, remember we spent most of the course studying these minimization problems where you have a cost and a constraint, and you set that constraint equal to 0. And if you have regular point, meaning this being non-zero, and if you have many of them, you want linear independence, right? That was one of the KKT conditions. And we have the Lagrangian being 0. Then, yeah, we have minimizer. Next week, we'll do a convexity for variation. So you computed the first variational derivative, and that was fun for you. Like I computed like 5. Everybody, they were like, do 15A. Like, I'll do it after the quiz. But yes, that was funny. But yeah, I did a bunch. Hopefully, you guys can you will do well today. So part B will be variational derivative, part A, Euler Lagrange. All right. Yeah, but okay, so second week we'll do second variation, which was the last KKT condition. And that will be it. So I will put one variational problem with constraint, and it will be first and second variation. And I think I will make the OD be very easy, like, because that's not the point. We're not 244 here. I'm not testing your Wolfram, your like, what is it, method of undetermined. So like in the quiz today, the minimizer is trivial. So don't, if you're getting complicated stuff, you're making a mistake. All right, so I'm not testing ODs here. So anyways, all right, good. So that would be the 3 questions as promised. Same difficulty as the midterm 2, but 3 hours. Yeah, because Mo said I have to do it that way. Yeah. If you want to blame someone, blame Mo. So he gave me the, no, blame me. I'm responsible. Yes. But anyhow, so you have 2 functionals. F will be the cost, G will be the constraint. And yeah, so we're going to talk about this stuff for now. All right. Let's go. So yeah, I will just talk about how you solve this problem, right? So what's the big difference when you fix the when you fix the this guy to be 0 and you minimize, right? So it will just be Lagrange. All right, let's go. So like we said, the thing you're going to compute today in the quiz, the variational derivative, is the analog of the gradient. So if you remember, Lagrange multiplier says set the Lagrangian to 0, which was just gradient plus lambda, the constraint. So we'll do the same thing. Oh yeah, you also need the unit regularity, which we'll check separately every time. So you need this k to be non-zero. Often this is trivial, but you need that. And that's it. So I'm going to prove that all you need is this condition. Okay, so it's not obvious, so I have to prove this for you. So let's do that. So what do? You yeah. So you change your functional. So going from, f minimum over integral of g0, you change it to a minimum of f plus lambda g. And you compute, you just use the theorem from before. So your new functional, call it, what do I call it? L? All right, fine. So L, come on. Let me change something here. This is stupid. So L will be F plus lambda G. And, oh, I see what I did. All right. Now I get it. So, and you can split it as lambda of F plus L of G. So in other words, my functional is F of LF and G of LG. So if you apply Lagrange, what do you have? You have a minus d dx of d dp of who? Of L of F plus lambda L of G. And then d dz L of F plus lambda LG, right? Is that okay? Okay, good. And I just used linearity to write this guy. Nothing hard here. Yeah, sure. I mean, yeah, so that would be the condition. So you just have to check, and I will do a bunch of examples that that will give you the ODE. Whatever, let's do it. Let's do an example. So you fix 2 points, minus A and A, and you take a curve of length L, so length L, and you want to minimize the area under the graph or maximize? What do you want to do? Okay, maximize. So you want to find the largest area under the graph. So you want to maximize this integral, right? Which is the area under u of x. From minus a to a. And you fix the length of the curve to be L. Okay? All right, good. All right. As usual, we don't like max. So we change everything to min. So we put a minus. And let's do this together. I mean, okay, whatever. So yeah, so I don't know, I can ask you. So what would be the L of F, XZP? No. Well, I mean, sure, but like, yeah, it's Z here. But then, yeah, and then, but yeah, yes, we're gonna change it. And then what about this guy? Yeah. Yeah, it's easy. So then, yeah, we make it minus Z and we have this. So now let me, I know it's easy, but I have to do it. So you have to, let me first say what the Lagrange is. So you have to do this, dp, and then of L of F, or minus F, plus lambda L of G, and then ddz of L minus F, lambda L of G. All right, so let me do this on the side. Yeah, so L of P is 0 because L of this guy is 0. There's no P there. And then the Z guy is, yeah, minus 1. So that's the F stuff. And then let's see, L of P of G. Yeah, so you do chain rule. Is that okay? All right. And L of Z, it will be 0 because it has no Z. All right. Let me make some space. Did I wrote it already? I should understand it. Yeah. Yeah. So when you plug all this stuff in, L of F is 0. L of G is all this guy, and this stuff is simple. Everything good? All right. And you set this guy to 0. So, and I integrate it. So then you get X on the left. Yeah, perfect. Okay? Is that okay? So we just integrate, we I changed my thing. I just integrate both sides. So, okay? All right. Why is it minus? Oh, because there's a minus already. Yeah, got it. All right, so yeah, you get this guy, which I had a way to do it. Now, yeah, whatever. Let me see what I did. Yeah, so you square it, that's easy. And then you want to rearrange. But how can you see it from here? Can you see it? So I have y squared, let me call it y, equal to 1 over lambda. Yeah, I guess you can just multiply both sides, right? So I just want to see how you can guess it. So you do this, and then you isolate for y. So I bring it to the left, and I have 1 minus 1 over lambda squared c1 minus x equal to this whole thing again, and you divide both sides. That looks terrible. Let me see what I did. So I claim that this u of x satisfies this implicit equation, so you cannot solve it explicitly, but it at least tells you that it would be a circle. So I want to do this with you. It's boring just talking all the time. So yeah, I will take derivative of both sides. So you get 2x minus c1, 2ux minus c2, and then u prime equal to 0. How do you think we can get? Oh, I see. Wait, what? I don't see a way. Fine. I don't want to look at what I did because I don't remember. I have it here. I don't want to look at my own slides. I want to like guess what I did. So how will I show that this implicit satisfies that equation? What do you think? Let's find out together. So how would you get it? Do you understand the question? Okay. All right, let me see. We claim this solves the differential equation. Guess you can sub in. So you have squared equal to lambda squared minus 2 squared. Yeah, I don't know. I'll just cheat. Yeah, so I took the derivative and then you rearrange it. Fine. So what? Wow, that's very dirty. So you have this. So this is easy. You just rearrange and then you square both sides. So far, so good. And then I'm guessing I plug it in back, right? What? You added to both sides. That makes no sense. And lo and behold, you get this. Wow. How can you even see this? This is dirty. So this guy is lambda squared u prime squared 1 plus u prime squared. And then they cancel out. Sure. Sides. Wow. Anyways. So let me, I wish I had some intuition for this. I don't. So again, yeah, so we want to solve this equation and we start with an answers. So this is the answers. And so you start with this, I call it, this is equation 1, not this. So you start with this equation, you take derivative, that's okay, right? That's not hard. So, and then you get this guy, that's okay? All right. And is that okay? You call what? Yeah, this is like how I made this guess. Yeah, it's a guess. Yeah, yeah, that's how it works. It's not my guess. People have done this. But anyhow, so you start with this guess, you take derivative, okay, and you isolate. So you take derivative, you by chain rule, you get u prime, okay, and you isolate for u prime. And then what's the goal? The goal is you notice that the guy on the right matches. Okay, so the x minus c1 and this guy are the same. And then there's a following dirty trick. You're like, okay, let me add this guy to both sides. So we add it to both sides. So it becomes 1 plus. And then this guy becomes u plus c2 squared, right? And this is equal to lambda squared by our guess. This is our guess answers. Okay? I know it's stupid. But then, so yeah, we do that. That's good. And then from here, you move it to the left. So you have u minus c2 squared equal to lambda squared 1 over u prime squared. But yeah, we use, where is it? Then we use equation 2. So this is equation 2. We use it over here to get back u prime. And yeah, so we put in back the u prime. So let me write it in detail. So yeah, so we have u minus c2 squared, x minus c1 squared. I don't like this. I will try to find a better proof. I hate this proof. Makes no damn sense. I hate these proofs when they're so abstract. It's just a dirty trick. And this guy is the guy on the right that you wanted, and here they cancel out. So you get x minus c1. Is that okay? Sort of roughly. It's just a bunch of tricks, which I hate. Math is not supposed to be like that. Sometimes it is, but I'll try to find out the logic. All right. Maybe Andrew has some, or Daniel. Was it Daniel, Andrew? Yeah, if you guys have some intuition, it would be great to hear it. All right. Anyhow, so we showed that the graph that has the maximal area connecting points A is given just by a circle centered at point C1, C2. So you have some circle centered at C1, C2, and that will give you the maximal area under the graph, and its radius will be lambda squared. And if you want to find the radius and the constants, let's do it together. So you plug in your initial data. So you have minus a comma 0. So that means minus a minus c1 plus c2 squared equal lambda squared. And you plug in your a, a0, yeah. So you have a minus c1 squared plus c2 lambda squared. Is that okay? All right. And then, but the guys on the right are equal, right? So right away you get c1 plus a squared equal to a minus c1 squared. Let's assume they're both positive. No? Can we just do that? So I have c1 absolute value equal to a minus c1. That looks terrible. So do I have to split cases? I just want to find c1. All right, let me assume c1 is less than a. So then you have c1 plus a equal to a minus c1. So you get c1 is 0. Fine, I don't care. So c1 is 0. So that means what? So get c1 to be 0. Then you have a squared plus c2 squared equal lambda squared. So you get your c2 squared equaling lambda squared minus a squared. So square root it. So I got my second center of circle. And then how do you think I can find the lambda? What constraint shall I use to find lambda? There's one more. Yeah, perfect. So where is it? Yeah, so we set, where is it? Come on. Yeah, so we set the length to be lambda. L. Let's say 1. All right. C1 prime, that's weird. C1 is no, if C1 is 0, that doesn't seem good, does it? Oh no, it's good, it's fine. All right, I thought it was. All right, what do I want? Yeah, I have to find this guy. So I have to find lambda. All right, and I know that 1 plus u prime squared will be, let's say 1, from minus a to a. All right, let's try to figure this out. So Oh no, this is way harder than what I'm talking about. Or maybe not. Okay, good. Or maybe. Oh, no, it's too hard. Can't do it. Can I? No, I can do it. Squared x minus c1 squared minus lambda squared. So yeah, I'll just tell you what the integral is. And if you want to integrate it, have fun. So you have square root of x minus of x squared. Isn't this like arctan or something? So, and then you have minus lambda squared and equal to 1, from minus a to a. Can we integrate this, or should I use Wolfram alpha? Oh, what is it? Arctan? Arcsine? Okay, let's check what Wolfram alpha is. So we integrate 1 over x squared minus a square rooted equal to 1. No, just integrate it. What is it? It's disgusting. What do you mean? So it's like this terrible looking log. I didn't say I would get you the number. So yeah, so if you integrate this, which looks disgusting, I'm not gonna do this. No, this is too much. So you have move the lambda to the left, to the right. So 1 over lambda, and then what do you have? A half of log x squared minus lambda squared plus 1. So it's a difference. No, let me not do that to you. Minus a half log, and then 1 minus x minus lambda squared. All good, good. And then you evaluate this in minus a and a. Is that okay? It looks terrible. I don't expect you to compute this. Even if you just stop here, I'll give you a plus. I don't care. This is way too hard to compute explicitly. All right, you can see what happens. All right. So what took us so long? We had to find all the constants. And so now we found that the radius of the circle will satisfy this implicit equation, which my guess is you will have to do this numerically. Maybe if you group the logs together, you take exponential, we'll see. But it doesn't look promising. Is that okay? Can I move on? All right. Is that okay with you guys? Daniel, who else? Andrew? All right. So yeah, I wanted to find the radius and the center of the circle. So it's a lot of work just doing that. All right, let's look at another. Yeah, it's fine. The full problem that motivated this is called the plateau or Dido problem. It's a famous problem in analysis and solved in all dimensions. And it says if you have a surface, so the general statement is if you have some surface in Rn and you want to find the shape that has the maximal enclosed volume. Okay, maximum enclosed volume with fixed surface area equal to L is always given by the sphere. So the n sphere in Rn. Okay, that's always the variational solution to maximum area for fixed surface, maximum volume for fixed surface area. Okay, if you want to have the most, you have to use a sphere. Okay, so, all right. So, okay, here's another problem. I didn't have time to type it, but I'll solve the problem with you. So here's the picture. The picture is you have 2 points in space again, let's say 0, 1, and you want to figure out if you fix its length. You want to figure out the shape of the chain. So imagine a bird. Choo-choo. There's a little bird, and I don't know, it looks like a mouse. What would be, suppose the bird gives gravity, what would be the optimal shape? Will it bend a little bit, or will it be this perfect looking shape? And it will be this shape, as you expect when you look at tree lines. All right, so you have 2 constraints. You will first fix, this is always the length, so you fix the length. All right, equal to L. And this one, we already talked about it, if you remember. It's the effect of gravity. So we also talked about it as surface of revolution. So this example of chain, hanging chain is the same as the catenary, the surface of revolution. Okay, so we're asking what the graph has the least, whatever you want to call it, surface area. All right, let's solve it. So let me make some space and solve it with you. So here's the problem: minimize y prime squared dx, given that the length is fixed. So 1 plus y prime, and let's say is equal to 1. Okay. So what do? You first write down the Polar Lagrange. So let's do that. Oh, yeah, let me ask you. So can someone tell me what would be L of f? Like, you know, XZP. Any ideas? Good. Yeah, and you already told me that. So, right. So these are the 2, and now let's find the Euler Lagrange. All right, minus d dx of partial p of L of f plus lambda L of g d dz of same guy, L of f plus lambda L of g. Is that okay? That's the Euler Lagrange. So you have minus d dx, and as usual, I don't know if you can, I can tell you, or if you can tell me, what do you think is L of the partial in P? What do you think? Same one. Hmm? Huh? Yeah. So you have, and then what should I plug in for Z in my Euler Lagrange? And for P? Perfect. And then, yeah, same thing. So I might as well factor it. I don't want to keep writing this. So you have u plus lambda times, yeah, u prime 1 plus u prime squared. And yeah, dz is easier. So what will be this guy? A bunch of things die out. Huh? No, no, no. There's no ratio here. It's dz. Huh? 1 plus what? Oh, but square rooted, right? Yeah, okay, good, yeah. So one per, yeah, exactly. And there's no lambda, or is there? Oh, no, there is lambda. No, wait. There's no lambda. Yeah, there's no lambda. All right. Oh, I don't want to look at it yet. Do I want to look at it? Mm, yeah, let me make some space. I want to do this with you. I don't want to. So what do? You integrate both sides. So you get u of x plus lambda times u prime. 1 plus u prime squared equal to minus the integral of 1 plus u prime squared. But what is that equal to? Yeah, yeah. So it was this constant 1, right? So yeah, yeah. So it's minus 1. Yeah. Is that what you want? Is that it? What? What is it? What happened? Yeah, the constraint is this guy, and I just integrate. So it would be, I don't know. I call it 1. Come on. For simplicity, I set it to 1. It would be minus 1. Jesus. Oh my God. Wow, we have a lot of material. Um, uh, oh, you're right. Are you right? Yeah, yeah, of course you're right. Because I moved it to the. All right, thank you. Good job. Good job. Okay, so why is there a u prime here? Did we make a mistake? Strange. Why do we have a u prime and this guy doesn't? Did we fudge? I don't think we fudged. We took derivative and it became 2p, right? So it's zp. What's the mistake? I wonder, what did we fudge? Is there no square? There is a square. Man, what did we do wrong? Z, and then we took square root, and then it's zp, and it's over that. But this case says, no, you have, let me check. What did we do wrong? Where was it? Where I took it from? Let me make sure I get this right. Yeah, this is one of your textbooks. Where did I take this from? I don't know. I don't know what we did wrong. I don't get it. So this is the problem. We did Lagrange. And then what did we do wrong? I don't get it. So we had this, and he has this. Why does he still have this? Hmm. What is my mistake? I don't know. So let me do this again. Yeah, this is y plus lambda of 1 plus y prime squared. And you have z plus lambda 1 plus y prime squared p. And if you take ddp of it, you get z plus lambda and then p times 1 plus p squared. If you get ddz, you get 1 plus p squared. So oh, I see, because I'm stupid. It's very simple. That's always the answer to life. Wait, what? Anyhow. Okay. So from here we substitute So I have y plus lambda equal to 1. He squared both sides. And now he isolated for d dyx. I'm going to keep the dy because it makes more sense to me. So, because this is what we derived, and what we derived is not wrong. It's just different. It will give us the same answer. So I have this guy, so I have to take it on the left. So I move it, and I have 0 equal to 1 plus y prime squared, 1 minus y plus lambda. And then I just isolate. So y plus lambda minus 1. So you have 1 over 1 minus, or if you like the other way, and then square root it, y prime. Is that okay? What? Anyhow, so from here you can do separable equations. So this is dy dx, and you separate. So you have 1 dx equal to square root of y lambda minus 1 dy. And here you integrate, okay? And when you integrate this, which is something, it's like x equal to, what is that? What's the integral of square root? Isn't it like 3/2? So 1 plus a half, right? Yeah, I mean, take derivative, whatever. So then you have y, come on, y plus lambda minus 1 to the 3/2. Yeah, whatever. I believe our answer more than I believe his. Good. All right. So that's it. Thank you. Are you guys there? Let me see. Andrew, can you use the mic? I wonder, Andrew?
Hello.
Did I make some mistake? I think we got this right? I don't see our mistake. No? Work. Thank you. Andrew? Oh yeah, there you go. What do you think, Andrew? Did we make a mistake?
I don't think we made a computational mistake.
Yeah, I don't see any mistake either. Let me see what's going on here.